start recording and say happy Thursday, everyone. It's almost Friday. Happy garbage day. Yeah, garbage day was Wednesday. That totally messes me up when it happens. I see the garbage truck and it's like, wait, am I teaching today? No. No, like that started during the pandemic when literally garbage was my anchor point for like whether I had to put real clothes on to be in my basement on Zoom or not real clothes to be in my basement on not Zoom, right? That was the difference. I had pierced ears that almost closed because I hadn't worn earrings in like 2 years because I had headphones on all the time. So, anywho, it's nice to be back in person, and thank goodness for things like vaccines that we can all protect ourselves with and yet still be people. So, hooray. I heard from a little birdie that there might be some homework questions. Might there be some homework questions that we can talk about? It's due next Wednesday. Hit me. What's your question?
For computing the odds ratio.
Yes.
For example, the question 42.
42. Making good progress.
What I did is to compute the odds ratio according to the question 40. Manually compute that. So I'm wondering if there is a R code to compute odds ratio, or we can do that like manually.
You can do it manually. The order of operations matters, though, for the ones that are for differences.
Yeah.
You need to get the logit slopes first, and then take the difference in logits, and then take an odds ratio of that difference. If you take the difference of the odds ratios, it won't work.
I can just use the function exp.
That's it.
In the parentheses, there is a node.
Exp, and then like in R, is that what you're using?
Yeah.
Okay, so exp and then point it to where the coefficients are stored.
Yeah.
I have a couple examples of that in example 2a where I've done that. There's also a dedicated function that makes odds ratios, but if you do it, so you would need to use GLHT to get the difference in the logit slopes, and then you save that output and do exp with that. Yeah. Or you can just get your calculator out. Either way, because if the p-value is significant in the logit metric, it's significant in the odds metric. You don't need the standard errors or the p-values separately for that. It's the same information. Yes.
I have another question.
Okay.
Question 76.
76. That's got to be that. Which section? Section 3? Okay.
And
okay.
the odds ratio is between 0 to 1, meaning the slope is negative.
That's correct. Odds ratios between 0 to 1 mean a negative slope.
Yeah, negative means harmful.
So in this case, do you want to have a job?
Yeah.
Okay. I'm operating under the assumption that gainful employment is a good thing. So if a negative slope makes you less likely to get a job, I would call that harmful.
Okay.
That's the way I would look at it. Now, we may not all like our jobs, but we like living indoors and eating food and having clothes and things like that. So jobs are a way to accomplish those goals. Sure. Other specific questions about homework? Okay. Well, I also heard that folks had some questions about how to set up the variables for homework. So in the example data, you have a variable that's called something like quant training. I'll just abbreviate it with quant. And there were potential values of 1, 2, and 3. And those corresponded to low, meaning you just did the bare minimum. 2, you did some extra training. Or 3, you took as many quant classes as humanly possible. Guess which one is the right answer? When I simulate data, I control the world. So there's a lesson here. But if you put the variable in the model just like this, where these numbers, again, I'll put the labels on here. Are these really numbers? If this is what they mean, they're not really numbers. Because these are arbitrary labels that go with them. Like I could have had 1, 20, and 45, right? That's equally valid because these aren't numbers. They don't mean anything. So if I put this variable into the model as a predictor, it will try to fit a linear slope for it, thinking these are numbers. Practically speaking, that would be assuming that the difference in the predicted outcome between low and medium is the same difference in the predicted outcome as between medium and high. It could be the case that that's true, but that's an assumption that we would want to test. In addition, if I put this variable in as is as a predictor, who is my reference for the intercept? Yeah, who, right? A 0. Would that be like someone who's never had any quant training, maybe? It could be a thing, but there's not in my data set. So it would be weird from that perspective too. So what I had asked you to do is to create two contrasts, or to create contrasts. There needs to be two because it's always one fewer than the number of groups, using indicator coding in which low is going to be the reference. So actually, let me put that back in here. So I would need to make a new variable. We'll call this variable 1 for right now, and variable 2. If low is intended to be the reference, what values should I give my new variables for cases that have a 1? Correct. 0 and 0. That sets the reference point. Because the intercept is the expected outcome when all the predictors are 0, this creates the low as who the outcome is for. Now I need to be able to distinguish each other group from low. So if I put a 1 here, this variable is intended to represent how far off medium is from low. So rather than naming this variable 1, I might name it something like L versus M. That's my notation for which is the reference is listed first. And if I want to differentiate low and high in this one, I might name this low versus high. So am I ready to go analyze data if this is what I do? No. What will happen if I don't cover all the possibilities? It will blow up. It will not work because the model is going to kick out cases that have missing data. So the only people who will be left is this group. It will kick out everyone else. So we fill the leftover cells here with zeros. So then what happens is, functionally speaking, if I only have this column in, does the predictor mean what I think it should if I put that in all by itself? No. What groups is it comparing if it's all by itself like this? What does this variable mean in isolation? Well, I still am comparing medium as one point, but I'm comparing it against both. So it would be the average of low and high versus medium if this were the only variable in the story. So functionally speaking, what happens is these two being 0, the second variable steps in to differentiate those two. So when they're all together, they have the right interpretations. This variable's slope will tell you how much medium differs from low. This variable's slope will tell you how much high differs from low instead. What if I had another group? I'm creating a new category. Not only did you take every class, you went and took classes in the stat department too. How about that? What do I need to do to make it work for 4 groups instead? I need another one. We'll call it low versus awesome. What goes here? What goes here? What goes here? What goes here? There we go. What goes here? What goes here? There we go. So it's always 3 predictors with 4 groups, 2 predictors with 3 groups, and one predictor with 2 groups. So this might just be talking about homework, but it's also going to be talking about our next half of this unit, how to predict ordinal outcomes like this. So you see how we had to set up 3 separate variables to cover my 4 groups? What if I wanted to predict who was likely to get each kind of quant training? The answer is 3 simultaneous but separate binary regression models. That's it. And how we set up the zeros and ones essentially tells us what the model is predicting. And that is going to be the hardest part about switching to categorical. But it's based on common principles of thinking about it as a predictor. Okay, questions, comments? Let me take out awesome for a minute here. Go back to this. If I asked you homework questions about this story right here, any homework question that involves the low group, you have in your output, because the model is phrased to directly tell you everything relative to the low group. So if I asked for medium versus low, that's the slope given by this variable. If I asked for low versus high, that's the slope given for this variable. But what am I missing? Medium and high, right? Well, it's going to be this variable's slope minus that one, because that's how I get from medium versus high. So it's a linear combination anytime a question is asking about differences for non-reference groups. They're implied by the model, but they're not given directly. You got to ask for them. Okay. Other homework. Similar concept, by the way. One of the first things I asked is, what is the impact of number of papers on your likelihood of getting a job versus number of posters? And then I asked for a comparison. If you only have time to do one more thing, which should it be? So to get a difference in slopes is, in this context, the exact same logic as getting a difference in these slopes to get the difference in the non-reference groups. Same algorithm, same logic, same everything. So I'm trying to push you a little bit to recognize additional instances in which the things you know how to do would also work. And comparing slopes like this when they're in the same units, the impact of one more paper versus one more poster is one such way you can do that. All right. Good on homework for now then? For now. You still got time. It's not due till Wednesday, because we just finished the stuff on Tuesday, so I always want to make sure you have a week or so. Example 2A should give you everything that you need in terms of the code to be able to do this. You just need to be able to modify the code to fit this situation instead. All right, you ready for something new that's not new? Yeah, sound effect. Slide 24. I've got like 3 slides and then we'll look at example 2B. So, too legit to quit. Who here was alive in the 90s? Anyone? Anyone? Few people? So,
yes, I was alive in the 90s.
You'd be surprised. So, too legit to quit is my joke, because this is an MC Hammer pun who had a song called Too Legit to Quit, and it had a hand gesture with it. Too legit to quit. And this video, which I have linked here, it's like a 20-minute video. The song doesn't start until 8 minutes in. It's like a whole movie. And this video is noteworthy because at the time, it was the most expensive music video ever made. And it has all these like 90s stars, like professional athletes and musicians and things guest starred in it. So it really is quite a cinematic masterpiece. But Too Logit to Quit is going to be our theme song because all of the things you just learned about logits directly translate into predicting other kinds of categorical outcomes, ordinal and nominal specifically. You already know how to do this. The catch is recognizing this translation to where we're going to take your categories and divide them up into binary to predict. So which way we set up those separate submodels is going to be based on what kind of outcome it is. So we call this generalized models for categorical outcomes with special cases of ordinal, where they're ordered categories, nominal, where they're not ordered. For those of you in the IRT class, anybody? Anybody in this class? Yeah? Polytomous IRT, that's what we're talking about today. That's the connection. So if we have ordinal data, we're going to use something called a cumulative logit. If we have maybe ordered data, there's an intermediate one called adjacent category logit. This is not used very much, so I didn't build an example for it, but I want you to have heard the words. And definitely not ordered or nominal is going to be something called generalized logit or baseline category logit, or multinomial regression is the words that go with this. So here's how it works. First off, ordinal. We're going to take the possible answer categories and create submodels to predict them, where it's one fewer than the number of categories. So for instance, if I have possible categories of 0, 1, 2, 3, I'm going to build 3 separate equations simultaneously. The first one is going to predict the probability of 0 as one alternative versus 1, 2, or 3 lumped together. The second one is going to lump together 0 and 1 and contrast that with categories 2 and 3. And the last one will lump together 0, 1, and 2 and contrast it with 3. With me so far? So when we learned what a logit is, right? The log of the odds of the probability, and I always say of a 1 because that's what makes sense. So if you think of it from that binary perspective, in these submodels, the red is like the 0, and the blue is the 1. So it's 3 simultaneous logistic regressions to break up these categories into binary alternatives. Which one you get, though, differs by your software. Some software is oriented in predicting the 0, and some is oriented in predicting the 1. And that's going to be the tricky part. So this is called a cumulative logit link because in each of these binary equations, all the categories are included cumulatively. All the data contribute to each prediction. In IRT land, this is called a graded response model. It is also known as a proportional odds model for reasons that we'll talk about in just a second. So if I were predicting these 4 categories in an empty model with no predictors, the empty model would look like this. On the bottom of the screen, it takes all 3. The logit of a response greater than 0, if I'm predicting the blue here, I can write it as y greater than 0 is e to the intercept plus over 1 plus e to the intercept. Same thing for the other submodels, but note we have 3 different intercepts, because the intercept gives us the probability of a 1, right? We have 3 different 1s in these models. So the probability of answering in any particular category is indirectly provided by the model. So if I want to know what is the probability that somebody picks answer 0, this first submodel tells me that. Because all I got to do is say, well, I know what the probability of a 1 is, so 1 minus that has to be the probability of a 0, because they sum. Likewise, if I want to know the probability of a 3, the last model was going to tell me that directly. It's 1 and 2 that are sort of buried in here. But if you look at the differences, if I want to know about a 1, I can take the prediction from the first model, the probability of 1, 2, or 3, subtract from it the prediction of 2 or 3, and then I've isolated what 1 is. Likewise, if I want to know about 2, I take 2 and 3, and remove 3, and then I've got 2. So you still get the probability of any answer, all 4 of them, even though the model is organized in this weird way. So let's look at examples with predictors in them, such as x1, x2, and their interaction. Note the subscripts. I had to come up with my own notation scheme for this, so what I chose to do is add the second subscript to refer to which submodel that parameter is from. So it's beta 0 in all 3 places here, because we're talking about an intercept. But it ends in 1 if it's the intercept for the submodel 1. It ends in 2 if it's that one, ends in 3 if it's that one. So the way that I've worded the equation here, I am predicting the probability that y is greater than 0. That's this submodel right here. I'm predicting the blue. The second one is y greater than 1, predicting this blue, and then y greater than 2, predicting this one. So note, these are greater than signs, not equal signs. So it's a little bit of a switch. Then the rest of it, I have an x1 predictor with a slope, I got an x2 predictor with a slope, and I got an interaction. What's not on beta 1, beta 2, or beta 3? Say it again. One more. I'm sorry, I can't hear you. Error? E? Yeah, there's no E's in here because we're still predicting binary where residual variance is not a thing. But in terms of the subscripts, is beta 1 the same beta 1 all the way through as it's written? Beta 2 is going all the way through. Beta 3 is going all the way through. What these models assume by default is that the effect of the predictor is the same across all the submodels. It doesn't matter if you're predicting greater than 0, greater than 1, or greater than 2. These models assume the slope is the same. That's what's known as proportional odds. I'm going to show you how to fix it and test it. Because this seems like an unrealistic assumption, that the same things that would predict why someone would be all the way up at 3 predicts equally so to get all the way from 0 to 1, right? It doesn't make any sense to me that that would be a default. All right, the distribution that goes with this. Do you remember the distribution that went with binary? We swapped out normal and we replaced it with something else. What was that word? Starts with a B. B-E? We'll play hangman. What is it?
Very close.
Bernoulli.
Bernoulli.
Yes. Bernoulli is a special case of binomial. What is it?
Bertolli is like
Bertolli.
pasta sauce.
Pasta sauce for binary. Yes. Bertolli.
You're never going to forget it now.
Exactly. So Bernoulli, special case of binomial for one trial. Bernoulli is also a special case of what's known as multinomial, which is Bernoulli for more than 2 categories. So it's a categorical distribution that has only 3 parameters, 3 means essentially, because once you have 3, you know the 4th because they have to sum to 1. So it's just the probability of the answer if that's what you got. That's the distribution. So the cumulative logit is what makes the model ordinal. Nominal is the other alternative along with partial credit. So here are the other choices. There's only 2 more. Adjacent category logit is what is used if you're not 100% certain that all your categories are ordered. So that might be used in something like, let's say that you have a test item where a student has to do multiple steps to get it right. So like they can't do anything, they're at the bottom. If they can do one of the steps or they can do one of the other steps, You're not, it's like they can do one thing. Like you're not really sure which one is higher or harder. But if they do both, then you know for sure that both is more than just one. So something like that, it's what's known as a partial credit model in the IRT polytomist literature. And it's the most intuitive thing I've ever seen. The submodels kick out the extra categories, and they model each of these conditionally. So given that you answered either 0 or 1, what is the probability of a 1? Given that you answered 1 or 2, what's the probability of a 2? And so on. So this is not cumulative. It is possible that you can have things that go out of order this way because there's no constraint about what happens for 2 versus 3 relative to 0 and 1. They're separate. Nobody uses this model though. Like I don't know why. It seems like the easiest thing. Part of the reason would be because if you have not many people, it can go badly. Like if only 3 people answered 3, then this submodel is going to blow up. The other alternative is for nominal or multinomial, and this is literally like dummy coding. This. You designate one of your outcome categories as a reference, and then each of the submodels predicts the probability of each other category. So given that it's 0 or 1, what's the probability of a 1? Given that it's 0 or 2, what's the probability of a 2? And you can work across the models to get all of the predictions, all the comparisons that you want. And that's it. Told you, like 3 slides. So how you tell your model if your outcome is ordinal or nominal is based on how you set up these submodels. What is the 0 and what is the 1? I'm doing air quotes to the people on YouTube. Because in cumulative land, the 0 is the red part and the blue is the 1. So these are different link functions to be able to set how you set up these submodels. Different links, but they all use the same multinomial distribution. Okay, want to see an example? Yeah, that's it. I mean, I don't have any more to say. I will tell you that your next homework is going to be on this. And I promise you there will be no interaction terms. I promise. Do you know why? Because it is hard enough to figure out what y is. I'm dead serious. And which way the model is going in terms of each submodel. So that's our only job for this example, is to figure out what is being predicted. That's the hardest part. Everything else, once you figure that out, is the same. So I'm building on example 2a, same data, same story, except now we're predicting the 3 category version of whether they want to go to graduate school, which I have labeled 0 is I'm not likely to apply, 1 is maybe, and 2 is I'm very likely to apply. Those are my labels. I have some description about why I chose certain packages over others for anyone who cares, but let's start with descriptive statistics. So apply 3 is my variable, and I'm asking for Pearson correlations for that. Are these really numbers? They're not. So does this really make sense? People do it all the time though. So the correlation between, say, parent degree and their likelihood of applying is measured in 3 steps instead of 2, 0.21 according to Pearson, 0.36 according to Polychoric. So we have the same thing that we talked about last time in terms of wanting to customize the type of correlation to the type of variable format that you have. And if it's an ordinal variable correlated with another ordinal variable, that's polychoric. So we have the same functions that I used before, polychoric as a user-defined package I found in Stata, and then the hetcore thing I found in R. So this is a repeat of what we had previously, but just to include it for the sake of completeness. Okay, so pay attention, everybody with me? I need you to remember these 3 numbers, okay? These are the percentages or proportions of people in each of these categories. I need to know this to know what the hell my model is doing. This is the answer key to figuring out what your software is doing. It is much harder than it should be. Here are the proportions in R. So first up, empty model. I'm writing out what the model is predicting in long form here. So the log of the odds of the probability of a 1, air quotes around the 1. So where the 1 used to be in here, it's a 1 or 2. The blue part is the numerator. The alternative is the denominator. So that's submodel 1. I can say this more succinctly as the logit of apply greater than 0. So I'm focusing on the numerator here. Likewise, the second submodel is the log of the odds of the probability of a 1, but now 1 is a choice of 2. And the alternative, a 0, is lumping together 0 or 1. Two means 1. It's not confusing at all, is it? I told you, this figuring out what the hell y is the hardest part of these models. I truly hate them, but the world uses them and you need to know them. So the way that we're going to solve this ambiguity of terminology is we're going to say the higher choice or the lower choice. So the higher choice for the first model is 1 or 2, and the lower choice is 0. The higher choice for the second model is just 2, and the lower choice is 0 or 1. So if my model is working the way that I think it should, then what I should get back are predicted probabilities that match this table. So the first submodel is predicting the probability of a 1 or 2. That's these two put together, 0.45 in proportions. That's what I should get. The second submodel, if it's predicting just the probability of a 2 instead of a 0 or 1, I should get a proportion back of 0.10. Here are the values of the intercepts in logits that you're about to see on the next page that make this work. So in Stata, I am using another user-defined package that I found, and I was so happy when I found this. It is called, to Stata users, gologit, I believe, because ologit is the package for ordinal, and G is to generalize it further. But I look at that, and to me, this says, go logit, go logit, go logit 2. Because go logit 1 was not good enough. We need to upgrade. So we're going to go logit 2. And apply 3 is my outcome. So this is my empty model designed to make sure that my software is doing what I want it to. So my first 0 and 1 is how it's labeling these submodels. My first coefficient here is negative 0.2 in logits. So this is the intercept that goes with, can I fit it all on the screen? The first submodel, this one. So in words, what the hell does this mean? It's the logit of what?
The logit probability of an answer greater than 0.
That's right. So it's the probability of picking something greater than 0, meaning 1 and 2 lumped together. It's the logit that corresponds to that probability. So if we unlogit it into probability, what's that called? You can't write unlogit in your papers. What do you write instead? Inverse link. Yes, the inverse link to go back to probability. Do you have it memorized yet? It's e to the logit, so e to the power of, divided by 1 plus e to the logit. Okay. Do I have it on here? I'm pretty sure I do. Here. Oh, I had it on the first page. That's where it went. Here it is. So what is this thing called? What do people call e? It's like Euler's constant or something.
Yeah.
There, I know it has a name. It's 2.71 with a bunch of decimals after that. But e to the power of, or exponentiate, the predicted intercept in logits divided by 1 plus e to the logit. So that's when I say e to the logit, this is what that's the operation that I'm doing. So that's my inverse link that gets me back into probability. Okay, zoom back out again for a second. All right, we're off to a great start. Now, what is this one? It's the logit of something. Say it louder. It's the logit that corresponds to the probability of 2 instead of 0 or 1. Yep. And so that translates into a probability of 0.1, which just matches the data. Okay, so all is good so far. And in Stata, I can say, hey, can you do that math for me, please? And it's like, no problem, dude. And it figured out for each category specifically. So it rearranged the submodels to tell you more directly what the predicted probability is from the empty model of any of these three answers. So these match the proportions in your data. They should. Now let me show you why I went to the trouble to find GoLogit. Here's OLogit. OLogit all by itself, the built-in Stata package. Do these numbers look familiar? 0.2 and 2.2. Isn't that what we had before? Negative 0.2 and negative 2.2. Do you remember why I love logits so much? They're symmetric. If I tell you that the logit of a 1 is 4, what's the logit of a 0 instead? Negative 4. So these things are not labeled intercepts or constants. They are labeled cuts. These things are thresholds. They are the point on the pretend underlying distribution where you are more likely to be in the higher category. They correspond mathematically to the logit of the probability of the 0 instead of the 1. Yes. Can you say that one more time, please?
So the reason we say the negative 2.19 here
Mm-hmm.
is the log of 2 because on the left side the result is 1. So this one means 2.
This one means 2. Yeah, so it basically you can think of it as where is the lower, like where's the boundary at? Like this is predicting after 1, this is predicting after 0. Yep. So if the probability of the higher category corresponds to this logit of negative 2, the probability of the lower category corresponds to this logit of positive 2.
So basically with either function you can figure out either.
You can figure out either. This will be a homework question. I am asking you to remember this principle. So this isn't so bad. It's predicting the other way, right? Like it's predicting the 0 instead. I can probably live with that. If I were to add slopes to this model, guess what they predict? Nope, they predict the 1. I'm dead serious. The equation is internally inconsistent. So I'm like, nope.
Why?
I'm going to nope on out of that. And I'm going to work with GoLogit 2, where everything in the model predicts the right way, the upper way.
Stata's normally better than this, so this does frustrate me a lot.
This is, so Stata at least has the decency to label these things differently. Do you know what they're called in SAS? Intercepts. These are not intercepts. These are thresholds. Now, cross-class collab happening next week. The SEM class is starting the IRT unit next week, binary IRT in particular. And when you fit binary IRT models in structural equation software, you get these stupid things. You get thresholds. So there will be 3 different versions of a difficulty parameter based on which version of the scaling you are in. But if you know what the probability of a 0 is, you can figure out the 1. So to get from the logit of the probability of a 0 to flip it around, you use what is known as an additive inverse. That means multiply by -1. I learned that. One of the students taught me that, I should say. I learned it by watching you. So we're not doing this nonsense. We're just not, okay? We're just not. In R, there are a number of packages that do ordinal regression, including a package called ordinal. Guess what it gives you? Thresholds. It has the same internally inconsistent structure. So I'm going to nope on out of that, and I found this one. VGLM. I don't know what V stands for. This is a massive package. It has 8,000 things in it, and the documentation is god awful. I had to spend so much time working through this. So you will hear a lot of snark because it frustrates me when I have to work that hard to find something that I know how to do and make it work. But to their credit, they have all these choices that allow me to customize the model into the version that is less confusing. I didn't say not confusing. I said less confusion, right? We got to have the right expectation here. So it looks like regular R code. I'm saving my model as an output called model3 empty, meaning predicting 3 categories empty model. Using the data from example 2, the family is cumulative. When you see that word, think ordinal. That is the name of the link function that gives you an ordinal model. And I'm using logitlink to do it. Reverse equals true. That is how you make it go the right way. I truly want you to reverse the model so that I get intercepts instead of thresholds. Truly. Parallel equals true, we'll get to in a minute. So here's what we get. Intercept. Thank you for labeling this correctly. But it labeled it as 1 and 2, not 0 and 1 like Stata. So this is focusing on the higher category, not the lower one. But we get the right answers at least. And this is me helping you. This is not R. No way would they print what things mean in the output. And then they tried to help you some more. This is what they printed in the output. Name of linear predictors, meaning what is the submodel about? It says the first one is y greater than or equal to 2, and the second one is y greater than or equal to 3. What's the highest category I have? Yeah, 0, 1, and 2. Highest is 2. And this is what R printed. The logit of greater than or equal to 3. There is no 3. R is just crazy. So this is me. No, actually, these are not the names of the linear predictors. I once had a discussion with a faculty member about whether software should be taught in classes. This person thought that if you really know what you're doing, the software is easy and you can figure that out on your own. Counterpoint, okay? I had to do a whole lot of work to get an empty model to make sense. I haven't even started modeling yet. So I'm trying to save you from this process of confusion. So we are going to have intercepts. The intercepts are going to predict the blue, the higher category, as the 1, and the lower category, the red, as the 0. That's how we're just doing it that way from now on, okay? Let's add some predictors. The same predictors that we had last time. So I have 2 model equations here. Submodel, by the way, is a term that I use. I don't know if that's a real thing, but I think it makes sense. So I don't have any synonyms for you. So the first submodel is predicting a score greater than 0, so predicting the probability of a 1 or 2. The second one is predicting a score greater than 1, which means a 2 instead of 0 and 1. In English, this is predicting the probability of at least considering grad school, right? It's not a no, it's at least an eh. And then this is predicting, yes, definitely going to do it, versus on the fence. I have separate intercepts across the submodels, but I have the same slopes. This is called proportional odds. In GoLogit 2, the PL option tells it to make all the slopes the same across submodels. So if I look at the results here, I like how Stata does this. It divides it up. So this is the model predicting a 1 or 2. This is from the model predicting a 2. Now, do you see anything in common across these 2 blocks of numbers? This exact match. Consequence or coincidence? Consequence. Yeah, this model forces the slopes to be the same. So if we look at GPA, for instance, this is the change in the logit for a 1 unit increase in GPA. The logit goes up by 0.62. Can we agree on that? A slope is always the change in y, the outcome, for a 1 unit change in x, the predictor. So if we put that into the story, this is the change in the predicted logit for a 1 unit change in GPA as a predictor. Now, is it the predicted logit of 1 and 2, or is it the predicted logit of 2? Yes, both. This model is assuming that GPA has the same impact on being sure that you're going to apply to graduate school as being on the fence. When you put it that way, like, why would you do that? But most software defaults to this, and it's very difficult to find packages that don't, which is why I had to do a lot of digging. The constant is the thing that gets to be different, because it's your reference point for the predicted logit when all your predictors are 0, based on the proportions in the data. Okay, how are we doing? Odds ratios. These are all positive numbers. Coincidence or consequence? Consequence, what's the scale of an odds ratio? It ranges from 0 to positive infinity. If your slopes in logits are negative, what is the range of your odds ratio to go with a negative slope in logits? 0 to 1. An odds of 1 is a slope of 0. Odds ratio of 1, excuse me, is a slope of 0. So 1 is the neutral point in odds ratios. That means you're just as likely to or to not. So then these are positive slopes up above. So they all have odds ratios above 1. Backing on out here. Now, I had a discussion after class last time. I think it was with you, sir. One of the other reasons I don't like odds ratios, these are supposed to be effect sizes, right? That's what people use them for. So I will give you a comparison of these two because these are both dummy coded predictors. And so it looks like, if I just go with the numbers here, that the impact of having a parent with graduate degree is a lot larger than the impact of going to a private university. Like those are comparable because it's 0 versus 1. What about this one? GPA is continuous. This is per unit GPA on a, I guess, 0 to 4 scale. What if I had an opinion such that I really wanted GPA to be the most important predictor? I could rescale GPA and change the odds ratio. So this is unit specific. This is per unit still of the variable. So in that sense, it's not really standardized in the way that we're used to thinking about effect sizes to be. So keep that in mind when you're thinking, oh, well, this one's not as important. How many units are there to move in GPA? There's 0 to 1, 1 to 2, 2 to 3, 3 to 4. This is for each of them. Versus a unit is the entire distribution of this variable, moving from 0 to 1. That's it. Okay. Right. Let's see it in R. Same setup. Apply 3 is predicted by these 3 variables. Parallel equals true is now of interest. What do you think that means? The slopes are the same. Yep. Because if you were to graph the predictions, the lines would be parallel. There's a shift and intercept only. And R, there's my 2 intercepts, and then it only prints 1 set of slopes because that's all I have. All right. Okay. How do I know if my model's any good? Yeah, -2 LL, right? So the analog to the F-test for the test of your overall model and regression, we do that with difference in -2 log likelihood. That difference in -2 log likelihood has a special name. Starts with an L. Likelihood, ratio, one more word. Test. Yes, LRT is the abbreviation I use for that, and the world uses. It's a likelihood ratio test, is what it's called. If you had the actual likelihood value out of the models, you would divide them. That's why it's called ratio. But because the models are estimated with the log of the likelihood, that changes the operation from division to subtraction. So it's the difference in -2 log likelihood, or it would be the ratio of the likelihoods across models. So I need to have, to do that, the -2 log likelihood from the empty model with nothing in it, because that's the worst you could possibly have. And then I can compare it to the one from this one. So I did that. with the function called ANOVA. The simpler model comes first, the more complex model comes second. And for whatever reason, it used to be like test equals LRT was the option. Within this package, it changed to something else. So I had to go digging in the documentation to figure out that type equals 1 is a likelihood ratio test. There's no way you would know that from looking at this. I know, man. A likelihood ratio test statistic, like the result of the -2 log likelihood, is treated as a chi-square. So the difference in -2 log likelihood between the empty model and this model is 24. So that is the test statistic, like a chi-square test statistic. That's how people would report it. And so then relative to a chi-square distribution with 3 degrees of freedom, this is the exact p-value. So the chi-square distribution has an expected value equal to its degree of freedom, if memory serves. So this should be like 3 if it were not helping. It's 24. So which model is better? If the difference is significant. Yeah, so here are your choices. Model 1 is empty. Everybody gets the exact same set of predicted values. Model 2 adds 3 slopes. If they are different, then you can say it one of 2 ways. The more intuitive way is to say Model 2 is significantly better than Model 1. The prediction has improved significantly by taking into account these 3 pieces of information. Or you could start from this as a reference point and say the empty model is significantly worse without the predictors. This test is done for you in Stata. Right there. There's your 24. And why is it 3 degrees of freedom? Number of slopes. Yep. Okay. How we doing? Yes.
So how do you interpret the 24?
How do I interpret it? It is the difference in height of your data as a whole under one set of model parameters versus another set of model parameters.
So like if it was 1 or something like really small, are we just basically, does it matter what the 24 is, or does it just matter if it's significant?
It matters if it's significant because what is enough depends on how different the models are. So if the models are different by one thing, actually, can I get out a picture real quick? What class would this be in? Okay. I know. It would have been in intermediate, I think. I need a picture. 1 second. Otherwise, I'll just pull up Wikipedia. Is it this one? Un momento, por favor. Oh. Did I get it? It's F. I don't trust myself to draw this picture well enough, so we're not going to have it. All right, nope. I can't find it quickly enough. We're going to Wikipedia, because that's where I stole the picture from in the first place. Ta-da! I want that picture. These are chi-square distributions as a function of degrees of freedom. So if I add one new parameter, then the distribution follows this yellow line. And in terms of the point where 5% of it starts, right, alpha of 0.05, note these distributions are one-sided. They don't have negative values because there's chi-squared. You can't. So 3.84 is the cutoff for 1 degree of freedom right in here, where 5% of the curve is. So if I added 1, then my chi-square needs to be 3.84 or larger to say that one thing contributed significantly. If I have 2 degrees of freedom, that's this green line. For that one, the critical value is 5.99 for where 5% starts. Yes, I have these memorized. You don't need to, though. Back in the day, we had to look up values on a table, you see. We don't do that anymore. All right, no. All software, even Excel, gives you exact p-values. But 3, which is where we are, is this pretty teal one. Cyan? I know. Yes. Cyan? Okay. Okay, cyan is for 3 here, and that one is 7.82 is where 5% starts. For 4, that's dark blue here, it is 9.49 is where 5% starts, and so on. I don't have the other ones memorized for 6 and 9. I don't have those, but does that answer your question? Like, it's relative to where 5% starts. Like, yeah, like this, it's unlikely that you would have stumbled into that section of the distribution if the null hypothesis that all these slopes were 0 were true. And at 24, we're way the hell on the right. So. Yes. Yeah, the 24 is the test statistic. And then the p-value underneath it. By the way, I don't like this about Stata. It prints p-values as exactly 0. P is never 0. So in your results sections, don't ever write p equals 0. That's not possible. It's p less than 0.000 whatever. I would just say less than 0.0001 in this case. Okay. So this likelihood ratio test thing is going to show up everywhere. Any kind of factor analysis model, any kind of IRT model, any kind of structural equation model, any kind of multi-level model. You will do this same -2 log likelihood difference thing over and over and over and over again. So do you remember the Legos that we talked about like at the very beginning of the semester? I have this Lego-based approach to how to teach quantitative methods. Lego number 1 is linear models. Lego number 2 is estimation. By estimation, I mean getting used to getting away from the idea of sums of squares as what we look at and getting into heights. We're dealing with heights under different distributions. And so when you say, like, I'm assuming that, you know, my data have a normal distribution, or I'm assuming they have this binary distribution, what you're actually saying is that's the formula I'm using to compute height. So if that's not an accurate description of your data, then that calculation of height is, as the kids say, sus. They do say that. My son says that word because he plays Among Us, where things are sus, with his friends at recess. That's what he does. He also called us out on discovering that the tooth fairy was not real. He's like, you know, last time I lost a tooth, you guys were acting all sus about it, and so I don't think the tooth fairy is real. And we said, yeah, you're on to us, pal. And then we're just waiting for the wheels to turn. Does that mean Santa Claus isn't real either? Like, sorry, dude. I never lied to him, though. His dad always had the best way of answering that question, like, is Santa real? Do you want him to be real? He would ask. Yeah? Okay. Well, then he's real to you. I remember finding out Santa wasn't real, coming home and laying into my mom. You lied to me. How would you lie to me about that? So anyway, back. Sus. What was sus? Where was I on this tangent?
The wrong likelihood.
Yes. Yeah, I was back talking about distributions. Yes. So that's what we're saying. Like if we have binary data, we pick this formula for height that goes with the data. If we have ordinal data, we pick a different formula that goes with that data. If we have a normal distribution, we pick that formula. So just that idea that you can switch out these distributions like Legos and make it fit, and the process of comparing heights is still the same. What you can't do is compare heights in different metrics. So you can't say, is the data under a normal distribution taller than the data under some other distribution? That doesn't work. They're not on the same scale. That'd be like saying, do I have more inches than I have miles? Like, it's not going to work. There's not a direct translation in that case. But anywho, I don't know that we have the strength for a non-proportional odds model.
Yes.
We can agree on that? So let's not do that, but just what's coming is, let's let the slopes be different and figure out which ones need to be different. That's not so bad, but that's not today. All right. Any other questions or commentary before we wrap things up for the week? No. All right then. It's Thursday, which means I say have a great weekend. Let me know if you need anything. Keep plugging away on your homework, and it will be due Wednesday. I do answer homework questions over the weekend if you are working on it. So you can always send emails. I will answer when I'm able.
I have office hours tomorrow at 10. You're
Yep.
welcome to come hang
Nikki
out.
has office hours at 10. Come party and hang out and do homework. Woohoo!